Som, som. Vamos entrando, pessoal, vai começar. Vamos entrando. Podemos nos acomodar já, vamos entrando. Daniel, puder me dar o apontador aqui? O sinal do apontador? Beleza, obrigada. Vamos entrando, pessoal.
So let's get in. Please, let's take your seats.
Vamos lá. Vamos acomodando. Bom dia a todos.
Hello, good morning, welcome.
Veloso. Pode pedir para a live, tá tudo certo? Pode pedir para já ligar a live? Daniel, TI. Daniel da TI, já pode abrir a live, tá? Sejam bem-vindos.
Welcome. So let's take our seats. Please come in, come closer. Have your seats.
Vamos lá, vai começar. Bom dia.
So good morning. Well,
bom dia a todos.
good morning, everyone. I hope you found a warm welcome. So I'd like to greet everyone here in person, but also those who are following us through our YouTube channel. Yesterday, well, thinking about what we had yesterday, what we have learned, what we've built, all the conversations, the workshop highlighted the technology and infrastructure, market, and business aspects of irradiation, bringing a Latin American perspective on the subject. We got to know institutions and companies that are already applying irradiation technologies and understanding how this market has been structuring itself. The panels highlighted the importance of sharing knowledge and joint efforts among the productive chain stakeholders. As we said yesterday, this is the moment Brazil and other countries in Latin America put together all conditions to increase its participation in this field. Today, we will keep in the same goal, integration and learning. For this second day, we will dedicate to the technological advancements that increase the food irradiation quality. We will talk about food security, process control, dosimetry, and expansion opportunities for that very technology. We thank all the attendees for your presence and for your punctuality. So, in order to start our agenda, we will have the first session to talk about advances in food safety technologies. As a moderator, we invite Mr. Rafael Rando that surely will enrich this debate. Please, the floor is yours, Mr. Good morning, everyone. Well, I'd like to start saying that yesterday was very inspirational. We had several presentations showing the current status of the food irradiation in Latin America, but it also brought some perspective on the plans for technology adoption in our region. The perspectives brought by the researchers and the manufacturers highlight that the subject is not going to be held not based on if we are going to use it or not, but about the demand and the size of the plants that we need to build. The discussions have shown the need of improving our regulatory framework to ensure a safe implementation and also building an environment of credibility and trustworthiness that can foster investment in this industry. We've closed the day of yesterday with a deep debate and very productive debate highlighting the necessity and the opportunity for installing this type of plants in Brazil and in the surrounding countries. A discussion that left in us a sense of urgency and excitement about the subject. So I'd like to reinforce the effort from Amazon to promote irradiation technology as a food safety tool in order and security to increase quality and improve exportation for new markets. So today we will start with a very technical content. So it's an honor to invite to the stage Dr. Ana Lúcia Villavicencio, researcher from IPEM, the nuclear. Ana Lúcia is a biologist, master's on nuclear technology, and PhD on food science at USP, a postdoctorate in Portugal in Bragança Polytechnic School. As a coordinator on the international agency, she's a professor of the IPEM post-graduation program. Acknowledged internationally, she's part of ABNT and Visa, always working with irradiation technology for food security and food safety. Today, it will be an honor to listen from her the speech on advancements for technology in food safety and food security. Please, Professor. Good morning, everyone. It's a pleasure to be here with you. Thank you. And thank you, everyone who is here. So let's go. So I'm celebrating. I need to summarize 35 years of research in 5 minutes, but okay, let's go. Let's try to do it. So here we have the SDGs, and they mean the Sustainable Development Goals. And they are part of 2030 agenda and a global pact, a global agreement signed during the United Nations meeting in 2015, signed by 213 member countries. We have 17 goals unfolded in 169 targets, aiming to overcome the main challenges for development.
Então, de repente, eu tiro pouco. Fico com medo, sou pouco surda já.
So from those 17, we highlight 8 goals, very important goals, and that perfectly fit on the food irradiation process. So, goal 2, zero hungry and sustainable agriculture, health and well-being, potable water and sanitation. This is very important for the food chain. A trust water, clean and accessible energy, industry, innovation, and infrastructure. I think this is the main focus of our meeting here. Decent work and economic growth, responsible consumption and production, and partnerships and implementation means of implementation. This last one perfectly fits what we've been discussing since yesterday, the sustainable development. So I bring here some considerations on the safe application of nuclear technology with radiation processing aiming phytosanitary, quarantine phytosanitary, agro sanitation, and food quality. So to meet food safety and food security, because food needing to be secure in order to have food security that will take lead us to food safety. So food safety that will lead us to food security. So promoting sustainable agriculture. These are new words in our research field because sustainability is a concept that focus on preserving natural resources, and it is defined as the ability to meet the current needs without compromising the next generations, reaching the balance between economic growth, environmental protection, and social well-being. The irradiation preservation method reduce microbiome contamination. So we all knew that, okay, for more than 100 years we've been working with irradiation, then during the 1940s, and so on and so forth. We had some improvements, and today it's quite modern. So we have the concept of food science. They are very important, and they change a little bit the perspective of acceptance. We have pest reduction, increased shelf life for fresh produces, for and well, this is a surprise. Everyone is always bringing the most beautiful food, so I brought the opposite. What may happen to food when it overcomes its shelf life? Even with irradiation, there are natural biocomposites that I will mention ahead. Well, we sometimes hear that irradiation is a miracle. No, it's not. Fruits, the food has a life cycle. So we need to meet that. And last month I was with Gerardo and we were talking about that. All the development from planting the seed, planting the seed by the farmer itself, and other machines that will select fruits in the same mature stage. So, I want to buy mango for irradiation. No, that's wrong. We need to have all fruits in the same maturing process, curing process, to process and irradiate it. Otherwise, we will find these harms to the food, and we will not be able to increase the shelf life. When we irradiate well set goals, then we'll have excellent results. Well, People ask in Brazil, do we have irradiated food in the market? Well, we know there is. They are not labeled, and the main goal here, I think so, would be for the bilateral agreements for bulk exportation. So here in Brazil we have spices as a food ingredient. So think, oh, I will irradiate the cup. No, no. Within this material, it has ingredients that were irradiated, ingredients that are allowed to be irradiated. They all follow RDC 21, the visa regulation, where it is written, but bad written.
In white in a silver paper.
No, white in a silver paper. They write white in a silver paper. So in the next review, we try to bring the Herradura symbol so that people can get used to this label. So ensuring consumers' health and food safety through certifications for international competitiveness. Well, we have this leaf infected by a pest, and this is a phytosanitary issue. So we have this cabbage leaf infected by pulps, worms. Because what happens that usually we commercialize this food as a ready-to-eat food or pre-packaged. We need to meet regulatory requirements for international trade. And we need to promote and raise awareness. We need to raise awareness on authorities and decision makers. This would be great impact. So, Thiago, I've worked with Thiago on international works about public acceptance. We have no problems once we explain the general audience what it is. The main problems rely on the decision makers. So this is a global tool for food safety.
And we have several treatment methods. We have cold conservation, and also we can do combined treatment, conservation using heat. We have pasteurizations, but these are treatments with no radiation, because radiation does not need thermal shock. So the pasteurization means a thermal shock. So how can we do this? Addition of conservants, non-conventional methods, high pressure application, chemicals, and the ionizing radiation. So we see that this evolving in its application, and also electromagnetic application. And this idea is already something defined. There is no need to discuss this. And I also approach the advantages of a process, because yesterday Gerard mentioned that the machine cannot be stopped. Hours of irradiation is loss of losing money. So we need to have business strategy, comparative advantages, state-of-the-art technology, and other qualifications for irradiation. And in addition to all these advantages in the process, we have the advanced technology for hydration, faster, reduction of time of baking, cooking, time for grains, more digestibility, and reduce the viscosity. So irradiation technology gives support to the chain of quality and good practices. We need good practice in the field. So we need to go start with the field, with the producer, everything well controlled and offering the opportunity to reach export market. It's a clean technology, quality and security, safety in fresh food, because only the food hygienized with chlorine, many times they are the pylorys where we have in our stomach. With irradiation, we eliminate this. It's another way of interacting. Compliance with export standards and trading process, and reduction of deterioration of food. And this technology is also connected with the sensorial part. Many people didn't know this, but this was well presented. And this sensory part requires the maintenance of odor, color, taste, and texture. And we have several sensory attributes, and these are the amount of applications that we have for a plant. We have disposable material and medical devices above 10 kilograms because they require sterilization. Pharmaceutical products, cosmetics, we know that some products of hygiene, personal hygiene products to be irradiated. Natural products, herb-based products, and vegetables and fruits we can apply low and mid charge up to 10 kilograms. We cannot use more than 10 kilograms. The expert committee concludes in a FAO document and with other Codex Alimentarius, the irradiation of any food up to 10 kilograms. We cannot sterilize a food. It does not present any toxicological damage, does not introduce no nutritional problem, provided it has irradiated with preview. And this food, using the good manufacturing practices, should be considered safe and nutritionally proper. This is a more innovative approach. The compounds, bioactive compounds, and the radiation can have positive and negative effects as any other process in terms of food. A series of factors can influence the effects. Here we have several types of carotene. Carotene is very interesting. It is in the products we consume, and in 6 months it is fresh. It's in the parsley we have. Every time every product has a chemical characteristic. The enzymatic darkening that we have with this caramel color, these papers show this, these studies, that it keeps the quality with a very fresh pulp. So not only the prevention of the darkening, and we also have several other types of food we developed in our lab in partnership with University of São Paulo, and we have a possibility of the interactivity with water that brings direct and indirect effects. We have several results that are very timely to the explanation. We also work with flowers for gastronomy. These are flowers with an interesting characteristic with a large amount of antioxidant, and flowers that we provide to restaurants. In the past, we used to put them in the fridge, but after some weeks, you have the eggs of the insects ecloding. Now, with irradiation, they last for 14 days because the eggs will not eclode. So, we have some components used by famous companies of cereal bars that use it. The components had eggs from insects, and this brought a serious problem. You could have the larvae already inside the food. In this quarantine phytosanitary project, and we saw this in Mexico and here in Brazil, this is well directed to produce with bilateral agreements to prevent the flies from the fruits. All the effects that has been published, and for eggs and larvae, you have the physiology change and the rate of development of these irradiated eggs when you have a well-defined range. If effects over pulps and the effects on the different species of fruits, and how to inform the consumer. We have the United States started with this. This is mandatory because there is no other method for food treatment. The irradiation is mandatory to eliminate Escherichia coli. We have this in Brazil, but nobody controls, so we cannot implement this. We saw these elements in spices and also in our food. We have the hamburger and several other examples. So the Latin American countries are well developed. Mexico, with their characteristics, because they border the United States, so wouldn't have so problems with Brazil, Uruguay, Argentina, because we are down. But we have the logistic part, which is not does not hinder Chile. Brazil rent the machines in Chile for the radiation program for some time and send the products to other countries, ship it from Chile. So we have several approaches, and that's why it is important, the legislation for the Mercosur. The main reasons is to have the detection methods to avoid frauds, to have traceability. One thing is labeling, and the other is the traceability. So for international trade, we need methods that will convey trust, confidence, control from the authorities, and protect the freedom of choice among consumers between radiated, non-irradiated organic products, and treated whatever is the method used. So we also work with the consumer's perception. We have some training for teachers of the basic school. For 6 years, we work with teachers of the public school. We tried to introduce this booklet with the Ministry of Education. We couldn't make it, but anyway, we have these booklets for children from 11 to 12 years old, and every time we have a training, some entity donates the printing of this booklet because we don't have the budget. And the consumer's perception of irradiated food is still a challenge. Well, ionizing radiation is an innovative technology that can be used in food safety and then to lead us to food security. Favors trading relations international in a mid-long term. Ionizing radiation can be used to preserve and improve bioactive compounds and the shelf life. The use of food waste is something promising, should be motivated, and is in the 2030 agenda. And the dissemination of this technology should be fostered. With this, I close my presentation. I thank IPEM, Cine, Amazon, and especially my work group. I have some students here, but this is the training with the teachers, the lab, the people working with insects, everybody working, and that's what we want to convey you. And we are available to any questions. Thank you.
Ana Lúcia, obrigado, parabéns pela palestra. Acho que palestra de nível técnico.
Thank you, Ana Lúcia. Congratulations to your. It is an honor. Congratulations for your presentation. We have some time for questions. If you have any questions, please raise your hand, and we will take the microphone to you. Thank you. Good morning, everybody. What a wonderful speech, just like the entire event. I have several questions, but I will just make one. Let's think in the hypothesis of animal origin products, whether in natura or processed. Considering the current regulation, is there any regulatory hinging to slot and then irradiate in the other place? Maybe it's obvious, but considering the Brazilian legislation, or considering that these products can be created in Brazil, is there any a problem in slaughtering in one place and irradiate in another plant? No, I think it doesn't have, because the plants have their good practices and control. This meat is put in refrigerated trucks. The food must be packaged. It's not exposed. So all this part of the cold chain goes with the irradiation process. And usually the irradiation plants, due to their size and complexity, well, my desire would be that they could be very close to the industry, okay? But it's not possible. There are products that could have it. You see, for some uh, industries, but for the food security or safety, it goes to a radiation plant. Is a different technology. It's something much greater than that. You saw yesterday the video showing the plant in Mexico, but I don't know of any hinder. We also saw the multi-purpose plants. In regulatory terms, is there any problem of the same plant in a certain moment irradiate grains, in another moment irradiates animal food, and then meat? Well, usually we separate food in a period of the day, those with a higher sterilization dose at night. Um, you, you need to have this production planning and to really take advantage of the time of that equipment. Do you remember Embrahad, an old plant we had in Brazil? In the beginning, uh, the the spices were irradiated. They were very interesting. They came and you have the odor. So today, oregano was irradiated. Another day was cinnamon. And then all the grapes that came later is smelling cinnamon. Well, this doesn't happen anymore. We have good practice, standards, regulation, a very big regulation. And also thinking about beef, for instance, or meat. If they are irradiated in Brazil, would be exported. Today, we have a bilateral agreement, sanitary agreements for several countries, and these agreements for beef exports result in international certificates that detail the agreements. Some countries accept the Brazilian certificate, others have their own. So, for irradiated products, is it necessary to change these bilateral agreements, or what we have today, considering countries like in Europe or United States today will be different? Well, it changed a lot. We have the FDA inspectors that work together for any bilateral agreement. We have already within United States, and it must be done as described in the process of this agreement.
So Brazil is in Mexico. If you're going to export to the United States, you need to pay the expenses for the American inspector and its own country's team of inspectors. But yesterday we heard something about, oh, if in Asian countries something. Well, in the past we have irradiated and the countries hires that service. So, for example, poultry should be slaughtered and go back to Mecca, but the irradiation process had no Brazilian inspectors, so the industry used to pay for that specific work, and you only did that at the plant, and okay. So there was no need of inspections or inspectors because there was no bilateral agreements. These are random service providing. So if they want to do, they bring their own standards and okay. Thank you. I could see that we have many other questions. and take the benefit of professor's knowledge, but unfortunately we will need to close here. But professor will be here during the half breaks, and we have email so you can send your questions, and professor will reply to all of them. Okay, thank you very much, thank you.
Obrigada, Rando. Por favor, volta para mim o conteúdo.
Thank you, Handu. Thank you, Professor, for your amazing contributions about the technology advancements applied to food safety. Now we would like to invite Dr. Patricia Villan to moderate the speech on R&D breakthroughs in food irradiation. Please, Professor, the floor is yours.
A gente pede só alguns minutos.
We kindly ask a few minutes so that we can set the connection so that we can move on. Just 1 second, please.
Daqui à esquerda. Pessoal, nesse intervalo.
Meantime, if you need the headphones for simultaneous translation, so please get your documents, go to the innovation room, and you'll find the table with our receptionist to provide you with the headphones. Thank you.
Ele está esperando para ser aceito.
Vamos aguardar aí 5 minutinhos, tá, pessoal?
Let's wait 5 minutes, please. Meanwhile, you can use this time for networking.
Ele está esperando para ser aceito no meeting, né, do Zoom. Acho que é só um problema aqui de alguém aceitar ele. Não. Mas ele está lá, ele está lá. Tinha acessado o link do dia 8.
Veja se ele recebeu o link do dia 9 agora que acabaram de enviar para ele, comandante Veloso.
No e-mail? No e-mail, né? Mandou no e-mail?
Mandou no e-mail.
E-mail, tá.
E-mail que já tinham enviado do dia 8, eu acho. Acessou só o link errado. Nós erramos em enviar o link errado. Vou ver se tem alguma outra
Eu vou
informação.
posso introduzindo ele?
Pode. Deixa eu só avisá-los que a senhora vai fazer isso, tá? Só um minutinho. Pessoal,
Please, we're just solving some technical issues, and meanwhile, Professor will introduce our speaker so we will know a little bit better about him.
quem nunca, né?
Well, it happens. So let's test your resilience. And you're going to take a look on your latest emails. You know, we are among friends here. So let's just wait a few minutes. Soon enough, he will be with us.
Bom, isso se fosse alguns anos atrás seria impensável, né? Tantas conexões. Bom, enquanto a gente
Meanwhile, let me start this panel. So, we are talking about nuclear science for food safety. And today we will hear from Carl Blackburn. He works since 2009 in food irradiation on the Center for Technical Nuclear Agriculture Technologies at FAO and the International Atomic Energy Association at Vienna. So he will talk about the R&D breakthroughs in food irradiation. This is a little bit of what we have seen at China. In China, China this year hosted a large food irradiation symposium, and together with other researchers, he has presented the most amazing things in this field. So, for example, breaking some paradigms, saying that some food could not be irradiated, but that today, with the right technique, for example, X-ray or lower energies, it is possible to do. So, almost everything can be done since you use the right technique and the right dose. Let's wait for the connection and watch Carl's speech so that we understand what's happening on research and development in this field. The international agency coordinates many research projects, as we could see at Selena's speech or lecture yesterday. And Carl is the technical official of some of those irradiation researchers.
A gente pode ter a alternativa de antecipar a outra palestra enquanto ele se conecta.
Almirante não quer.
Não quer?
Mas a gente já está em cima da hora, né? Ok. Tá chamando de novo. Ai, Paulo.
Ele não está ali na tela, mas ele está
He's not in the large screen, but he's in her cell phone. Okay, let's wait a few more minutes. These are issues of technology.
The one you have to get the link for today. Let's see if I can send to you via email, okay? Just one second. Okay. Yeah, thanks. Sorry. Entendeu? Tem que mandar para mim para eu mandar para ele, que ele não está recebendo por e-mail, não.
Ah, tá bom. Qual que é o e-mail da senhora?
É o pati.ita. Veloso tem.
Ah, tá bom. Eu vou passar ali para os meninos que o Veloso não está aqui. É Pati.
pati.ita.w.
Pessoal, é o seguinte, a gente
Well, we have an interesting alternative here. So, as we have an important doctor here, we have the possibility to explore doctor's knowledge while we settle this technical issue. She will be here soon, so we can resume our session, okay? So let's use this time for the questions of to Professor Ana Lucia. Thank you. Professor Anna, good morning. My name is Marcus. My mother is also called Anna. Well, thank you for all the knowledge you've brought us today. Congratulations to you and your team. My question is, do you know any coffee irradiation initiative in Brazil or Colombia? I mean the main producers. Well, the Colombian people, Venezuela, Costa Rica, they are all in our group. Well, some years ago we had, if I'm not wrong, before the pandemic, 2019-18, we had some people from the coffee lab. But then I've tried to look for them. I think during the pandemic the group was over. But now my student, João, that will replace me, he works with waste coffee waste, and he's working in cafe with cafe in São Paulo. We've tried to have some works with cafe, but cafe has a serious problem of aflatoxin. But we also have the solution once we combine radiation with a higher water activity, making the environment wetter, so that we have a combined treatment. With that we can eliminate the fungi. The toxin, no. Once the toxin is there due to storage issues or even the field, we have a lot of fungi in vegetables, but it's also a problem of good practices. So when it is not solved as it should, we can eliminate that fungi with 7 kilograms doses. So it is in the allowed range for food. Okay, thank you. We were able to establish connection with Professor Carl. So I am quite surprised with your generosity. Thank you for your empathy, people. So let's move on. Thank you very much.
Vamos lá. Carlos conectado.
Professor Carl is already connected. Okay, so let's get started.
Bom dia. Oi, Patricia. Yes.
Hi.
Now I'm with you.
So, okay, you have your screen here. We can see you. We can hear you. So you can start, please.
Ladies and gentlemen, thank you for waiting, and I hope you enjoy my presentation. My name is Carl Blackburn, and I'm going to talk about R&D breakthroughs. First of all, I'll just do a quick introduction. Then I'll just remind you a little bit about food irradiation, but I'm going to dive then straight in to food irradiation. So, quick introduction. You know my name. This is where I work. I actually work in a it's a unique thing in the United Nations. I work in the joint program of the Food and Agriculture Organization and of the International Atomic Energy Agency. Here you can see on the right our two DGs, DG Rafael Mariano Grossi and DG Q Jong Yu. So that's IEA and FAO. The joint program has been around for a long time. We had our 60th birthday last year. You can see in the middle picture on the bottom there. We're headed by an FAO director. We're based at the IEA headquarters in Vienna. We're both FAO and IEA at the same time. There are 5 sections. Another unique thing is that each section has its own laboratory. So now just let me remind you about food irradiation. I know you've heard a lot about this, but of course, irradiation just means shining things onto things. So you can irradiate food with infrared, you can irradiate food with microwave, you can irradiate food with ultraviolet light. But here, when we talk about food irradiation, we're talking about a special kind of energy beam. We're talking about using beams that can break chemical bonds. So this is ionizing radiation. There are 3 kinds of 3 sources that you can use: gamma, which of course from cobalt-60 mainly; electron beam from electricity; X-rays again from electricity. And it's quite simple in process. The longer you expose something to the radiation, the higher the radiation dosage, the more energy is absorbed by it. But let's talk about research, okay? Here you'll hear me use some language from the International Atomic Energy Agency. I will talk about CRPs. When I talk about CRPs, I'm talking about coordinated research projects. And over the last 10 years or so, we've been very much involved in 2 areas. One of them is what we call machine source radiation. This is using electron beam and X-ray radiation. And the other one is for phytosanitary treatments. You heard from Ana Lucia there some discussion about phytosanitary irradiation. So first, let me just say a little bit about this CRP. This is a CRP that's finished actually. It's about electron beam and X-ray applications in food irradiation. Of course, every program has an objective and it has results that has to be achieved. And I'm just going to run quickly through these. So first of all, the research is over. The results were published in 2022. It's very successful. Lots of people involved, lots of research publications, and lots of people got PhDs and MScs, etc. And we had some key mark results that I'm going to take you through quickly in the next few slides. Of course, we also had a pandemic, but I'm happy to say that it didn't disrupt the research too much. So something that came from this was new devices. These are some new devices that came from China and from Vietnam. On the left there, you can see this X-ray machine. It's an airport scanner that's been adapted. And it's been adapted in that the radiation it uses is X-ray radiation. But it's been adapted through some clever computer programming to make the adjustment so that the output looks like what the box of products would be if it was irradiated by an electron beam. So this is an important tool. If you have a commercial electron beam facility, you want to spend as much time as possible irradiating products, because this is money, right? This is a commercial operation. You don't want to stop your beam unless you really need to. Well, occasionally you have to stop when you do a new product because you have to dose map a product. You have to know how to properly process it, so you have to do some tests. Now, anything you can do to minimize that time helps. It saves money and it helps you run the facility optimally and properly, and then make sure you're treating things correctly. So this device on the left, this X-ray device from China, it's where you can play about. You can see what configuration, how you present the product in the electron beam. And then when you actually do the quick test run in the electron beam, you save time. So it's quite clever, and you can see, let me see if I get my clicker on. You can see from here the visual representation of the box. You can see it's green, that means it's okay, it's good to irradiate. So this is a good configuration, and it gets a nice dose distribution. Whereas in this box, you can see you have some black spots. This is bad. It means that this testing device is saying, if you irradiate this with electron beam, it's not going to process properly because you won't be able to treat these areas correctly. They won't receive the correct radiation dose. And here, this is a commercial facility in China that I visited relatively recently. And here you can see in the corner is the device that's being used. So it's very nice to see. So through this research, the company developed a commercial device several years later. And now this device is actually being provided and sold to electron beam facilities. On the right here, this is a different kind of machine. Here in Vietnam, they used the gamma source to do the same thing, okay? Here they looked at how the gamma radiation diminishes through the box. And from that, they could do some clever electronics to model the dose distribution through the box. And again, so by using gamma here, and then some clever calculations, you can work out what the dose profile, the dose distribution would be if you were to use an electron beam. We also had some new techniques. On the left, you see here we talk about low energy electron beams. Here we're using what we call soft electrons. So normally we have mega electron volts, like millions of electron volts energy. And here, the trace in black is the loss in the number of microorganisms when you irradiate with a conventional high energy electron beam. But if you use much lower energy, so this is 300 kilo electron volts, actually you can get pretty much the same profile, okay? It's not perfect, but with white peppercorns, with black peppercorns, with things like nuts and dried ingredients, you can see that you can get a pretty good reduction in the microorganisms. And why is this useful? This is useful because you can put these low energy, these soft energy electron beams, you can put them in factories, you can put them in packing houses. But the high energy beam, you can't do that because it needs more shielding to be safe. This only works because the microorganisms are on the outside of the peppercorn. So the low energy beam doesn't go all the way through the peppercorn, but as long as you can make it go on the outside, on the surface, then you can treat sufficient microbes to make this a viable technique. On the right here, you can see a similar thing. This is using soft X-rays, low energy X-rays. This is in a hospital. This was research in Korea. And what happened here is they used this soft X-ray cabinet to make sure, to doubly make sure that fresh food for immunocompromised hospital patients is exceptionally safe to eat. If you have hospital patients who don't have, their immunosystems are not working correctly, you have to be very careful because even the slightest infection is dangerous to them. And one of the problems is that their diet, because it's usually highly cooked, highly processed to make sure that it's clean, it tends not to have very much texture. So it's soups and soft foods. And the only way that you can make sure that they can eat things like fresh vegetables, maybe ice cream, is to use ionizing radiation. Because ionizing radiation doesn't increase the temperature of the product. And this is a nice case because they're using soft X-rays. It's an X-ray cabinet that's available in hospitals. And they're doubly making sure that this food is safe to eat because they irradiate it with soft X-rays. It's more than a nutritional thing. Of course, these people are very ill, and the patients, it's a boost, right? They really look forward to different foods, and they miss the food that has the nice mouthfeel, the nice texture, the nice crunch. And we all like sours and fresh fruits and vegetables, right? So this is a really good research output. Again, using soft beans. We also had some novel foods produced. Here's a product from Thailand, which is a pickled ginger. It won an award actually in Thailand. It's used in Thai cuisine, Thai cooking. But with more and more of the population working, and I have to say, it's usually the ladies who do the cooking for the household. With more and more cooking, there's a need to have a product that can be bought in shops that has a long shelf life. And they had an irradiated pickled ginger product that meets those requirements, and so it can be bought in shops and used. Otherwise, people have to pickle them at home and use it quickly. But now there's a shop-bought product that can be made. It's also been shown that you can use irradiation, and this is E-beam irradiation, for other kinds of pickles. In China, they used the research opportunity to switch. They used to irradiate a snack. They have a chicken feet snack in China. They used to irradiate this with the gamma radiation, and they did some research really to demonstrate how to switch, how to use electron beams instead of gamma beams to treat this commercial product. And they also again looked at pickles in Sichuan. Sichuan's famous for its fruit pickles, and they use electron beam to improve the shelf life of Sichuan pickles. In Pakistan, they switched from, they compared X-ray and gamma and E-beam for things like long life spicy meat products, for fruits and fresh vegetables. And in some other countries, they also looked at phytosanitary radiation and just making sure that electron beam, gamma, and X-ray didn't have any special effects, okay? And what we see from the research is that it's the dose that counts, not the type of irradiation, right? So it's the energy delivered per kilogram of food that matters, not whether it's an X-ray or an E-beam or a gamma ray. We also did some improved dosimetry systems, and we also did a little bit of work on safety of high-energy X-ray radiated food. I'm going to look at number 6 first, because I think in Brazil, I think you're interested in this, maybe with some changes in standards or national regulations, because currently in international standards, the maximum, or at least at the time a few years ago, the maximum was 5 mega electron volts for treatments using X-rays. Because above 5 mega electron volts, you start to get a different process that happens. Below 5 mega electron volts energy, the X-rays cause ionization. The X-rays just split chemical bonds, you get positive ions and negative ions. But above 5 MeV, you start to get another process. It begins to be more possible that you can induce radioactivity into food. You can make the food radioactive. But how important is this? And is it really a safety factor? Well, for many years, people have done calculations and people have tried to look. There's lots of modeling studies. All the modeling studies indicated that it shouldn't be a problem. It should just be a minor thing when you go to 7.5 MeV. And there's been several studies in the literature, and we did some more studies in France through this work that we were doing. And in France, they used a much more modern way of simulating the irradiation, so new computer codes. And right now, we actually have the technology. So there are 2 facilities in Europe which could irradiate using these high-energy X-rays. They actually use 7 MV X-rays. And very quickly after they irradiated the sample, we could look to see if there was any induced radioactivity. Here on the bottom, you can see before irradiation, and you can see some of the natural gamma emitters. You've got the potassium-40, which we all have inside us, and we all know it's a natural radionuclide. And then you have some radionuclides from the uranium and thorium series, these natural radionuclides. When you irradiate the food, you can actually see a few things. You can see here's manganese 56 and here's sodium 24. But you have to irradiate them to a very high dose. This is a 120 kilogram radiation dose, much higher. It's 100 times higher than you would irradiate fruits and vegetables. It's 10 times higher than you would irradiate meat. So it's much higher dose, and you do get traces of these things. But these are very short-lived radionuclides, and in a matter of days that you can't detect them at all. They've got short half-lives. But we use this research to double-check the calculations that have been done before. We also did it to work out some data where you can predict the yield of induced radioactivity for P radionuclides. And we also did it to double-check that it was safe and effective. And yes, we found that it was safe and effective. And we actually used rabbit food to simulate food. I know it sounds strange, but we needed a food that had a long shelf life, so it will keep well. We didn't want it to spoil when we're doing the experiments. And we also needed a food that had a huge range of different elements. And so actually, this rabbit food was pretty good. We looked at the composition in chemical elements, and it had everything we needed. So we could be sure that everything was there when we irradiated it, and we would see any weird and wonderful radionuclides if they were induced. On the left is some work we did looking at dosimetry. I think we're going to hear about dosimetry later today, but also with low energy electrons and low energy X-rays, there's a lot of work needs to be done on new dosimetry systems. This work, also in France, was looking at using a conventional alanine dosimeter system and having some correction factors. Once you get below about 200 keV for the energy of the X-ray beam, the dosimeter becomes less effective. And actually, so it reads about 95% of the radiation dose at 168 keV. And then when you go to lower energies, you start to read less and less of the radiation dose. So doing this very careful quantitative work, we could provide some correction factors for people who do low energy X-ray irradiation work. So, the impact. The research from the CRP did make quite a lot of impact, and the top one you'll see is the main one. We actually changed the international standards. So now, for phytosanitary radiation, the International Plant Protection Convention, and I'll show you later, now has increased the energy allowed to irradiate fresh fruits and vegetables. So now you can use 7.5 MeV X-rays. So we added to the body of evidence that said that was safe and effective. And lots of countries now, India, USA already allowed 7.5 MeV X-rays, but now lots of countries, Australia, New Zealand recently shifted to allow 7.5 MeV X-rays. China, Korea, Indonesia, and I haven't checked, but I wouldn't be surprised if a few other countries have also moved to accept 7.5 MeV X-rays. So the work has impact. It's also led on to more work where we've looked at low energy beams in more detail. But in the next slide, I'm going to tell you a little bit. Oh, here's the actual change in this is the international standard. This is the International Standard for Phytosanitary Measures, ISPM, number 18, requirements for using irradiation as a phytosanitary measure. This is what it said a few years ago. X-rays up to 5 MeV energy, and this is what it says now. X-rays up to 7.5 MeV. So the energy limits here for the E-beam and the X-ray are to prevent inducing radioactivity in food. And 7.5 is just as good. It does happen, but it's trivial. It's a minor thing. Now I'm going to talk about phytosanitary irradiation. Here we do research campaigns periodically because it's very important. And this, the coordinated research project that's ongoing right now, and in fact Anna Lucia, our previous speaker, she is a participant in this research. It follows on from some research we did in 2016, and what we're trying to produce is validated generic treatment doses for phytosanitary treatments. What do I mean by that? Well, there's another phytosanitary standard here, international standard. This standard had annexes, which are the internationally agreed treatments for regulated pests. There are about 43 treatments, and 20 or so of those, about half, are irradiation treatments. And usually these treatments, the irradiation treatments, are specific to one species. But what we're trying to do, we're trying to get more treatments where we have one radiation dose that can cover a whole group of different pests. So not just one species, but perhaps a whole group or a whole type of insect or pest at once. What's the breakthrough in this area? Well, the breakthrough is, now that we've got generated lots of data through research, the breakthrough is we can use this approach, a species sensitivity distribution approach, SSD. And this is a curve. You look at the data, you can construct a curve based on the radiation sensitivity of the species. So here we're looking at mealybugs. These are mealybugs here, and the effect is that we stop the mealybug from being able to breed. So in fact, this is the radiation dose that stops the next generation of mealybugs being able to reproduce. Okay, so these mealybugs live, but their children can't breed. So this is why we can stop them spreading through international trade, through phytosanitary radiation. And if you look, if you've got 14 different species, you can construct this curve and you can use it to work out which radiation dose would be the one that you need for a treatment that might be for all mealybugs. Obviously, there are millions of different species. We can't test every one, but if we get a representative sample, then we've got a statistically secure way of trying to get a treatment for all mealybugs, even though we can't do research on them all. It's also a clever tool because you can see that these two species here, the radiation distribution is sensitive on these two ones, right? So we can focus in on these species and do more research and see if the actual treatment dose is effective at less than 200 gray. What often happens when people look at how pests react to radiation, they have jumps in dose, so they might do 0, 50, 100, 150, 200, 250. And they find that, okay, at 200, yes, we can stop these the F1 generation from being able to reproduce. But the previous dose in the experiment was 150. So actually, although they might find that some could breed here from this species, it might be less than 200, somewhere between here. So by focusing on this species, we can bring, maybe we can bring the dose down further. Now I'm going to say about another CRP that's ongoing, and I put this picture there because this is all about soft electrons and soft X-rays, the low energy beam work. It was so interesting in the previous work that we did that we decided to have a a research project that would focus solely on these soft beams. And why? Well, it offers an interesting future, right? Right now, when you talk about food irradiation or irradiating any other product, medical products, etc., right now you have to take the product to the factory, right? So lorry loads of products go to the irradiation factory. It goes in the big warehouse on one side, it's irradiated, and then it comes out of the warehouse and goes on a lorry on the other side, and it's shipped off. But what about with these soft beams? You don't need all the shielding to protect you from the radiation. It's not so intensive. So here you have a device. You see these two canisters? This is a soft electron beam lamp, and you get dried ingredients. So you can have dried seeds, dried peppercorns, dried nuts, dried spices or whole spices that fall through these lamps, and they get irradiated as it falls through from both sides by electrons. So the throughput isn't as fast as a big conventional irradiation facility, but it can be fitted on a conventional production line. So what's the breakthrough here? Well, the breakthrough here is we're finding it's useful. For X-rays, we're finding soft X-rays have many different uses. On the left here is an old irradiator in Japan. It stopped working a few years ago, but for many years it used to irradiate potatoes to a very low dose, 60 gray. And the low dose was to stop the potatoes from sprouting. But it used cobalt-60 gamma rays. So this is where the cobalt-60 is. The potatoes process around, they get 60 grays, and then they come out of the facility, they're packaged, and they don't sprout. But the work at Dalat University in Vietnam showed that actually you can use, this is just a research setup, this is not a commercial setup, but they used a conventional little X-ray cabinet, and they showed actually what's important is that the radiation dose of 60 gray is delivered to a depth of at least 8 millimeter inside the potato. So by doing this research with low energy X-rays, they've shown that in fact, you can see in the diagrams here, you can prevent sprouting using soft X-rays, which is probably a good way to go for the future. Also, we had some people looking at another interesting product. We had people looking at eggs, whole shell eggs. And this is using soft electrons. Soft electrons don't penetrate very far. If you think about increasing the energy of a soft electron, what starts to happen is the electron can go further and further into the egg. Here you want to treat the eggshell, so you can use an electron of about 250 kilo electron volts energy, and it will irradiate the egg, but it won't go through the egg. So here you can see an untreated egg. Here you can see egg from a whole egg that's been irradiated with a soft, low energy E-beam. It looks identical, right, to the non-treated one. It's because it is. It's because the egg inside the shell hasn't been treated. And here there's an egg that's been irradiated with an electron beam conventionally. And here you can see the yolk is a little bit more yellow, not orange. And also the yolk's a bit runnier. And that's because the electron beam's gone all the way through the egg, including the yolk. And 6 kilogray was enough to bring about some changes to the yolk. Why it's important is you're really targeting the eggshell. If you look at the microorganisms on the eggshell, you can use soft electrons to target the eggshell. And a dose of around about 4.56 kilogray to the eggshell brings down the number of microbes. And it's important for things like E. coli and salmonella. Why is it a breakthrough? Well, we all know where eggs come from. Even with the best kept poultry flock, it's difficult to prevent microbial contamination on eggs because of where the egg has to pass when the hen lays the egg, right? Goes past where the hen pooper-dooper comes from, so you can't help but get contaminated eggs. And now here's some more up-to-date work from China and Japan. On your left, you can see this is how people conventionally treat the surface of eggs. So it's washed with a solution, sodium hypochlorite, which is good at sterilizing the eggshells. But it's a problem as well, right? Because you wash them, you have to dry them. So here the eggs are on an egg conveyor. So the eggs rotate as they go through the wash. And then when they come out the other side, they also have to be rotated as they're air dried. And you have to dry them coolly because you don't want whole hard-boiled eggs. And it's all to get rid of the salmonella and microbes on the surface. But here's the E-beam device, right? So this is the prototype one. There's an electron beam lamp running underneath the conveyor there. You can see it better in the schematic. This is an electron beam lamp. It shines electrons up. As the conveyor takes the eggs over the electron beam lamp, the eggs are rotated. And you can see the operators are stood here while the thing's running, so it's perfectly safe. It's not a radiation hazard because it's quite a low energy beam and it's not going to affect anybody. And they found, what did they find? Well, they found it works. In fact, not only does it works better than the sodium hypochlorite wash. And actually here the throughput can be quite fast. And it saves energy, it saves money, it saves space. It's a smaller solution to the technological problem. You don't need to dry the eggs because there's no liquid involved. It doesn't involve any chemicals, and also there's less energy needed because, as I say, you don't need to dry the eggs. So it's a good use of technology. So, ladies and gentlemen, eventually I joined you, and I talked now about research in machine source radiation. I talked about one of our breakthroughs, and one I want you to remember is this one that allows 7.5 MeV X-rays. It's a huge step forward, especially for phytosanitary irradiation of fresh fruits and vegetables, because 7.5 MeV X-rays are produced more efficiently than 5 MeV X-rays. The old standard, when you produce X-rays, you fire electrons into a metal target. You lose most of the energy as heat. So maybe 3 or 4% are converted into X-rays. If you use 7.5 MeV X-rays, you still lose a lot of energy as heat, but you roughly double the efficiency of the X-ray production. So you can get about 8% X-rays, 9-10% X-rays from 7.5 MeV X-ray treatments. So, ladies and gentlemen, I hope I'm back on time for you. Thank you for your patience and thank you for listening to me. Please let me know if you have any questions.
Obrigada, Carl, pela sua brilhante.
Carl, for your brilliant presentation. You really inspired all of us in the audience and those connected through YouTube to run other researches. Much of what you had said is already published in scientific journals and can be accessed through ResearchGate on the web page of the national agency. So thank you for bringing this industry answer. The industry needs research that will meet the needs of the work to optimize it with lower costs and healthy. So now I will turn to the audience to see if there is any questions. Well, we still have a very few time, so if you have a question, send through the chat that we will ask Carl. Carl, again, thank you for your commitment to the innovation for food irradiation, and the support you give to the members of the national agency, and over the time you've been in the agency, you were very successful, and we are anxious to have you here in Brazil. You have promised that.
I don't know if you heard us. Waiting for your visit in Brazil.
Yeah, well, I'd like to come. I'd love to. In fact, I'm sorry I can't be with you now. It would be lovely.
Yeah. Okay, so thank you again, and another round of applause, please, to Carl.
Thank you.
Thank
Sorry
you.
for having to wait. Sorry for waiting.
Thank you very much. Muito obrigada.
Ciao.
Tchau, tchau.
Thank you. Thank you for the contribution and so rich and complex information we are learning today that is strengthen the role of continuous interaction. We have now our coffee break, so please, we have 30 minutes.
Daniel, pode me dar o apontador?
Você tem como abrir a coisa dela? Só antes da gente começar, aquela funcionalidade do Zoom que fica a pessoa com uma tela pequenininha aqui, compartilhando a tela com a apresentação, você sabe fazer? Porque se ela não souber, a gente vai ter que explicar. Ah, tá, background, beleza. Tá, só conectar com ela só pra gente fazer o teste. Madame Marie-Hélène, can you hear me? Eu não tô ouvindo, não. Tá desligado. Ah, tá. Mr. Demon, can you hear me? And to hear us, we need to have a test here for the link. Yeah, your microphone is off. If you could turn it on. Professor Marie-Hélène, can you hear me? I'm Johnson calling you from Brazil. I need to test your link. If you could turn your microphone and camera on. Are you around? Professor Marie-Hélène, can you hear me? Are you in a room? So I'd like you to turn your microphone on in the camera so that we can test the link.
Hello? Do you hear me?
Yes, I can hear you. How are you?
Hello.
Sure, how are you? We need to test your link just to see if everything is okay. So you're controlling the presentation from your room, isn't it right?
Hola.
Professor Marie, can you hear me? I can't see you, I can hear you. Your microphone is on, not your camera. Can you turn on your camera, please? Excellent, now I can see you. So I would like you to use the following format for your presentation. Do you know how... Can you hear me?
I heard you.
Too many noises?
I can hear you, but I hear you one time and another time.
It's echoing, isn't it? Tá dando eco. And can you hear me now?
Yeah.
Okay, I'll use the chat. I'll use the chat to communicate with you, okay?
Oh,
Can you hear me better now? Is it okay now? Excellent, good. So what
yeah,
we need you
now
to
it's
do,
okay.
excellent, good. So what we need you to do is to use the,
No. Oh, I hear you
no,
again. The same
it's
phrase.
echoing,
No.
isn't it? É, tá dando eco. So it's
No,
probably
no,
your
no, no.
connection. It's okay here. I'm going to be in touch with you using the chat, all right?
Hello, do you hear me?
Professor Mahilan, can you hear me? We can't hear you.
Yes, yes, I
Okay.
can hear
Did
you.
you understand the
Do you
instructions?
see? Yeah, yeah, I hear you.
So you need to close your presentation and reopen in a different format. So let's do it together. We have the share button, okay? Can you press it now? Down there at the bottom of your screen. Yeah, use your mouse. And then you see all the controls down there. The share button is there. Just like this. Yeah, it's a green arrow pointing upwards.
Yeah, yeah, I see that.
Exactly.
Share the screen.
Exactly.
Ah,
When
ben,
you
là, il
press it,
essaie de me guider, mais
exactly, and then you see the layout. So on the right side, you see
oh là
four
là, et ça
choices.
c'est impossible. J'entends à nouveau ma phrase au bout de 3 minutes.
Exactly. The format on the right side, you see as the background. Yeah, or when you see presentation over your shoulder. Did you understand the instructions, Professor? So when you're sharing your presentation, when you press it, okay, to share your presentation, you see options. Can you?
Just a minute, please.
Okay.
I tried to stop the echo because each
Okay.
phrase is repeated 3 times.
Oh, okay, I understood it. So we're going to be in touch and using the chat.
Pardon? Ouais, là, je parle là dans le micro, mais je fais aussi dans le téléphone parce que sinon, je t'entends pas. Ah, ça y est, j'entends ma phrase à nouveau décalée. Oh, et ça y est, je m'entends dans le micro, dans la casque, mais une minute après, quoi. Enfin, 20-30 secondes après. Oh non, c'est insupportable. J'enlève le casque?
Som, som. Beleza, achei o microfone. Agora só me dá o apontador. É estranho falar dar o apontador, né? Não, não, dá acesso ao apontador. É que a frase é muito grande. Obrigada. Obrigada. Vamos entrando, vamos nos acomodando.
So please, let's come back. Let's have your seats, please. Please, let's come back from the coffee break.
Daniel, TI, achei. Estava lá no fundo. Vamos retornando. Então, quem tirou a foto foi o Almirante Newton. Tinha lá no começo. Decidiu por foto agora. Não, porque o Newton falou que não precisa de foto. Mas aí vamos falar novamente com ele. Se pode, a doutora Patrícia quer que tenha uma foto no final? A senhora pode se apresentar. Sim, é só uma pergunta sobre a organização. A doutora Patrícia agora quer que tire uma foto, aquela que a gente, acho que a gente não queria tirar assim. Tira aqui dentro, tira lá fora. Tá. Tá bom. Tá bom. Depois da palestra do senhor. É isso? Tá bom.
No final dá, né?
Tá.
No começo que não dá.
Tá bom.
Depois que ele fechar, aí as pessoas vão vir aqui e tirar uma foto.
Ótimo. A sua é. Deixa eu ver. Não, não, a sua é depois dessa.
Sim, mas é a última.
Penúltima.
A penúltima.
Tá bom. Pessoal, vamos dar continuidade.
Okay, let's resume. I hope you have enjoyed the coffee break as a moment for networking. So let's resume our agenda with a session about quality control. microbiological and sensory analysis of irradiated products. What such an interesting subject. Now we will invite Professor Tsai to moderate this session and to guide the discussions. Please welcome, Professor. You have the floor. It is a great honor to be here with you. I will speak in Portuguese. Our speaker is French. I am professor from the USP, and my nickname is the Atomic Ant. So let's go. Dr. Marie Desmond is a agronomist engineering and a PhD in food science. So it's quite related, agronomy and food science. She graduated in Strasbourg University studying meats. So she has a quality presentation with an interesting fact. She is the creator and the founder of this French technology center. Always worked in a partnership with the International Atomic Energy Association in Strasbourg. Currently, she develops strategic techniques, and she will present the experiences that she has with microbiology and sensorial analysis. So new products that we can export or human food. She's developing collaborations with in industry and academy. So she works in the market, but she also works with the academy. So these are roles that can evolve from what we see today and what's being done to reduce the prejudice against radiation. It's important to tell you that because we need to teach people that this technology, it is a technology that we've been developing in order to provide people access and to develop acceptance. So the acceptance on that technology so that we can have a safe and sustainable food from field to farm, from field to table. So these are new facts that we being able to see here. So I would like to thank your attendance, and we will start with Dr. Marie-Hélène. Okay, she's already here.
With us. Can you start now? We have 30 minutes for you. It's okay? Please? Okay, acho que ela vai. Okay.
Yeah, good morning, everyone.
Okay. Well, good morning.
Yeah, do you hear me?
Yes.
Good morning. Do you hear me?
Good morning. Can you? You can start. Yeah, we are waiting for you. Okay. Please start.
Oh, I hear my.
It's okay, Dr. Mahilan. We can hear you perfectly. You may start right now.
I start, but excuse me because I hear my own phrases 3 times. So, thank you, Doctor. Okay, I will try. Okay.
Do you have YouTube open in your computer? Is your computer with YouTube window opened?
Ma'am, do you have YouTube window open in your computer? or any other window rather than the Zoom window?
I don't know. I don't see where. I don't know where I have to go. Zoom window. Oh, I hear me.
Ma'am, can you hear me? Hello, ma'am. This is the interpreter. Can you hear me?
Miss Marie-Hélène, can you hear us? Miss Marie?
Yes, I hear you, but I hear also me back. Yes. Yes, I hear you.
Miss Marie, let's try to change your time for the next section, and so you have time to solve
Ça
these
recommence. J'arrive
technical
pas, et là, je
issues.
suis en plein présentation.
Would you like to try to speak without your phones, without your earphones? Just don't use your earphones for the moment and do your presentation. Just use the microphone close to your mouth when you speak. Não. Cara, vamos para outra sessão, tá? Vamos falando com ela aqui.
Tem alguma coisa errada nela. É de lá. Alguma coisa errada lá. Aqui, nenhum dos outros aconteceu. Alguma coisa lá.
Miss Marie, we are changing the order here. We will start a new panel, and we will have time for solving these technical issues, okay? Thank you.
Som. Som. Pessoal, vamos voltando aqui. Esses palestrantes têm muita sorte de ter uma plateia tão empática. Estamos aqui definindo se vamos antecipar a próxima apresentação
enquanto a nossa palestrante resolve lá os problemas de conexão. Som. Um minutinho, por gentileza. Pessoal, vamos voltar aqui para o nosso workshop.
So let's resume our workshop. Let's follow the next presentations while we define the best situation for our speaker, Professor Marie-Hélène. So thank you for your for being understanding with our event. I will invite to the stage Professor Camila Rodrigues Melo. She will moderate this panel on irradiation process control dosimetry. So, Camila, please.
Olá, muito bom dia.
Hello, good morning. It's been a great morning for us. And I would like to invite Dr. Carmen Cecilia Bueno. It's an honor to introduce her. While I introduce her, a round of applause to her, please. She has physics degree by PUC São Paulo, master's degree by PUC São Paulo, doctor by PUC São Paulo, and doctor by on nuclear energy by IPEM, and a postdoctorate by the Coimbra University. Senior researcher at IPEM with more than 30 years of experience on radiation dosimetry, published 140 articles, and has oriented many master's, doctorate, and postdoctorate students. She's the manager of the Radiation Technology Center at IPEM. So, Professor, the floor is yours.
Muito obrigada. Eu agradeço o convite para estar aqui com você.
I thank the invitation for being here with you. As we are in the last day, I'd like to congratulate the amazing technical scientific level of this agenda and the speakers that came before me. So, on behalf of Commander Veloso and Dr. Patricia, I thank you because being able to put together this audience with so different knowledge and still having an effective outcome, as we can see, it is a demonstration not only about your experience but the willingness of making things right. So I would like to greet you all because those connection issues many times do not come from the place we are. So let's take all the advantage of this moment, the benefit of this moment, and if the problem is solved before I finish, I may come back to my seat and wait. This is part of our hospitality and the understanding of technical issues that are part of event like this one. So I have here where I should click to. Oh, here. So I found some difficulties because this is quite technical, and I've tried to summarize here because I know that you all know radiation processing and its main applications, but this is just to bring a context on the importance of dosimetry, as Professor Paulo said before me. I want to talk about dosimetry in the radiation process and tell you that this is a well-established field. It is in the industry that, aside being a new area, it's always finding new challenges. So in the radiation processing dosimetry, we have well-established protocols. So for those who are from this field of study, this is a motivating universe. We can talk about the control on radiation processing. So this is an everlasting source of knowledge. The dosimetric systems, the conventional dosimetric systems, I know I have a different audience here, and I'm here to tell you that things are well established. And I will bring some provocations that Professor Call already brought. And the second provocation that comes from a less than 1 month experience on computing dosimetry. Computing dosimetry, it's a well-established element of our on the medical field, but for our field is a great challenge. So on the last 36 years, I went from experimental nuclear physics and now high dose dosimetry. So just for context, every time we talk about radiation processing, regardless the area, we are talking about products. A variety of products that are irradiated by gamma, electrons, X-ray, then have as a goal to preserve or change the characteristics of that very product. But for a heterogeneous community, this is our mantra. There's no definition like that, but I like to say that. For sure, without making them radioactive. So all radioactivity has a goal, always improving quality, adding value, contributing to the economic part, and to reduce the impact of some materials in the environment. So we know that this is a very a area of great advantages and very important in order to reduce socioeconomic inequalities. This problem is not reduced to the food field. For all fields, I need to ensure that the physical, chemical, biological effects are reproductive. It's fundamental to be able to reproduce the process. And how to do so? Through a rigorous dose control. But I've opened my speech talking about my field of study for more than 30 years. Having dosimetry as a core parameter to ensure quality and provide security for that irradiation to be conducted regardless the area. And we have different fields here. I will not dive into any of them. 70% of industrial applications of processing irradiation are related to medical devices sterilization, human health, polymers modification, most of them related to health, and food irradiation. Well, this one you know well. So this is a core importance application for developing countries or even developed countries. So this is a world concern. Well, we have some problems here. We have challenges for dosimetry as well. So if we look at the standards or guidelines, the problem raised is always the fact that we have elevated doses, hundreds of kilograms. And Professor just has shown us that for food, we have a different problem, complementary but different. the specificity of food irradiation. We have very low doses for food for process irradiation processing, high for medical physics. But being low take us to look at the dosimetry with a different perspective. So we have some current challenges. Facility variations, irradiator design variations, being them the gamma radiators, but also the electron accelerators and the X-ray conversion. So there are some challenges that 10, 15 years ago we didn't have. So I need to answer to those challenges, even because dosimetry is core. Without knowing it, the product will be not ready. So mainly for food, we have some potential human health implications. So I need to have that piece of information. So I told you what dosimetry is, but how and when I know that I'm performing the right dosimetry? Well, this is the basics. What I want from that product, what's being requested to the dosimetry professional. I need to ensure, in collaboration, I need to say, well, the effect that is being requested need to be met. If it's based on the absorbed dose, I need to ensure that. But there are standards, there are studies, and in the case of food, it's much more complex. There are maximum and minimum values that comes from previous researchers. And those researchers tell me that they tell me the maximum and the minimum doses. But now safety means minimum dose safety is that the dose I ensure that with that minimum dose the effect will be met. And the maximum dose means for each irradiated material we know what cannot happen. So if it's a glove for sterilization, it cannot lose elasticity. So it brings some diversity when we want to work with dosimetry. The dosimetry role is large, but this is not mentioned. Dosimetry starts when the facility is installed. So when you start in facility, and when I talk about radiation facilities, not only the accelerator, not the cobalt irradiator. I'm talking about everything, moving, irradiation, the belt, how the product will go through the radiation. This is what we call facility qualification. So the dosimetry responsible person is with the technician, and there are some conditions settled there. So there is the assembling, there is the qualification. So here I have, a 4 millimeters diameter beam. So for example, we have different ways to measure. We can have a film in the outside, in the out part of the beam, and I will measure that, and that will be part of the design. So in the first item, installation qualification, I have dosimetry with the manufacturers. So they have the techniques, but the operational qualification is, well, here dosimetry is very important. One process does not exclude the other. So I need to show that I want a dose range, for example. In that dose range, I need to say that everything is working properly, but the machine needs to be working properly. So in a gamma facility, it's much simpler. Of course, there is the logistic purchasing the material. Okay, but I'm talking about using the temporizer, the transit dose. I need to know the routine for that process, the rack position where I put my routine sensor. But when I'm talking about e-beams, then we need to ensure electron energy variations, the trail, the dose. There are phenomena that will impact the scan beam width. And when we're working with industrial scale, we need to enlarge the range, the area where I can add the products. And this beam is scanned by a frequency, and that frequency will define the speed with which the material will go through the ionizing area. So with beam width, beam height, we all do that with dosimetry. And the product itself, I need to check the product qualification. I need to set all the process parameters. Some products during irradiation, it needs to be hidden, from below by ionization that will hit that product, and sometimes that will have some impact, not only the dose. There are different techniques for different products, and here we have a healthy challenge.
But this problem is very big in high absorbed doses. In low doses, it's not complicated to keep the temperature of irradiation. And also, I need to map the product dose. Usually, when we irradiate whatever is the product, they have a uniform density, at least. But what would be the optimal? I have a radiation system from the beginning to the end. The received dose is the same. But this is ideally. This is translated into a parameter which is dose uniformity rate. This DUR. If DUR is equal to 1, meaning all the points of the material were irradiated with the same dose, we need to get it closer to 1. And we have many dosimeters, and we have 3 methods. The thermal one is the basic and simpler, but this is the beginning. The interaction, you have interaction with the material, converts to temperature. You see that this will be the dosimeter, in industrial, except for many groups. When you have this specific team, we use the calorimeter together. But if you go to industry once in a while, it's enough. And we have the chemical. Chemical is the one that dominates almost of the 100% of dosimetry is chemical. We have some information that creates my dosimetric standard. And physical. This, when the irradiation interacted with no just like ionization. So the conductors, they have many scales. That's why we have this X. There is not in the relation or list of recommended dosimeters because none of them stand radiation damage. So we have these physical effects. I forgot there was a stair here. So we have these dosimeters. We have the primary standard, the one that I showed you, that it gives me the measure of the absorbed dose, the calorimeter. And then we have the one that measures water, because the dose of these measures is this has water as a standard. And we have also the metrologic high quality of this reference standard. When you have a transfer standard, I have a dosimeter gauged in a NPL, primary lab. If I have a second lab that is going to use alanine, I can bring the alanine and caliber or gauge these new dosimeters. And transference, we can send it by mail because it has a great stability. And the routine, in your part especially, requires the dose mapping and process monitoring. So we have films or slabs for polymethyl methacrylate. So we have a variety does not end. Every new product, we have the people from polymers trying to find new materials. So as a primary standard, I have things that I put here, so I'm not affirming that this is the single one or it's better. No, this is the one I have in my lab. Okay, no advertising. It's a necessary disclaimer. When we are going to use for electron beams with energy between 6 and 10 MeV, this is the dosimeter with a HISO, where you put the material thermally isolated in a plastic foam, and you measure the temperature. That is irradiating, and I see this. I can use a thermopire, a platinum resistor, something that will give a good measure. Usually in the operational qualification phase, we need to use the calorimeter because it will give me direct information. We have it from graphite and polystyrene. Graphite for lower energy. You need to think because it's not off the shelf. Now, the transfer and reference alanine standard, we have the physical principle of alanine, and the EPR is obviously a principle that is for physics and nuclear physics, because involves streaming, pairing, and absorbed energy. I'm not going to go deep in this, but it's a system used everywhere. And you don't need to know how it works, but you need to be trained to do this. So we can measure, and we have a great variety. We have in Brazil a group developing the alanina pellets. They are calibrated in the NPR in England, which is the standard lab, and this blister type are essential to the industry. And this is another one. The light of the laser. Well, but anyway, this is the bench spectrometer and the alanine samples, and this is the best we have. Paulo mentioned briefly and talks about alanine. The other are the routine dosimeters. Those, when you go to industrial process where the cost-benefit relationship must be taken into consideration, we have very cheap ones, the cellulose triacetate, and it goes from the medical area to high energies. And for all of them, we have the absorption of the ionizing radiation, and depending on the matter, it can create free radicals, color centers, molecular complex, and we've been studying with this. Every time it changes, we need to study again. A plastic that becomes colored sometime later, depending on the storing conditions, it can fade. And this is something well known by the industrial area. We study this for many years, and we know what to do to establish the chemical reaction between them. This is an example how the clear dosimeter comes. It's very characteristic, and you see here, I put it segmented because we cut it in stripes to put it on the reader, and as it absorbs the dose, the color is altered. This is a dosimetric standard, and I can do the relation. So in the case of the CTA, that is essential for those who work with electron beams, these need to be present. The color is well defined that I showed you in the example, but the dosimetric person needs to know every material has a color induction. If you were to analyze them, you have a specific wavelength. It cannot be in the same doses, the same color. So you have well-defined wavelength. For CTA, 280 nanometers. You use a spectrophotometer, like we use in the chemical industry. But if you're going to irradiate 1 meter field, you have to cut the slice at the right dimension of the reader holder. I tried to find a competitor, but we have this from Ariel. When you look at this is small one that you can hold in your hand. We have the spectrometer connected to a software that reads the data for calibration. So I will measure 1 meter of a beam. So I irradiate. We have a roll of a Fujifilm transparent film, and we have a sensor that runs it. So I read 1 meter within some seconds connected to a software. I'm not saying this is the only one. We have of other brands, but that's what we have in our lab. So this has simplified our life, and you can still cut in stripes, but it compromises the spatial evolution. So if you get 1 centimeter by 1 centimeter to get the 1 meter length. So this is what we have right now. Polymethyl methacrylate. I have here what we use. These are our information. So we have some students doing this. We have the PMMA with several types covering high absorbed doses is the same we use. If you have a gamma installation together, we use it elevated. The experience will tell which is better for that application. And we also have the radiochromic dyeing films. This base is used for UV sensors, especially for children to protect the skin. It's the same principle. What changes is the type of dye we use. We need to know, we need to study. We study for fading the better range, but again, I use the spectrophotometer to measure it, and allows me in that small equipment, and everything is simpler. And what do we have? We have GX, RISO, FWT. We have more. We have others. But this RISO, which is Rizubit 3 and GX, you have a variation. One goes to 150, the other is 1 gray. But Riso and GX is almost the same material because the wavelength is very close. In 552 and 554, the material should be the same, with a slight difference due to the color. But you can see, I can include a barcode with that information. This is important to the industry. This is what they call the label dosimetry, and this helps a lot. And this is the experience of those who work. When you have a new product, you say, I'm going to start with this analysis, but also always with other to complement. So any installation can use this for establish and analyze the problems, and they are cheap. This is important for the industry. We can choose, okay, but we map the dose with this for a package that have something inside the box. When I do that, who is going to use my service knows that they cannot change the positions because I did the mapping. And if the density is not uniform, be careful. The measure can be wrong. This is a problem. When the problem is the process is defined, the problem is solved. But the problem is that we have a variety.
So it's a leaf. If it's that leaf from a different food, we need to rethink the dosimetry. So many times this demands hard work, but we need to do so in order to ensure that the dose is there. But well, the world recently got brave enough to think, okay, computational dosimetry. Most time of my life, and I'm experimental physicist. So I've built my career measuring well, studying well, and publishing only the experimental results. But now it's different. We have a computational dosimetry advancement where one will not replace the other, but rather it will help the other. So in our field, we have the reference. This is not my work. The aero team's part, and Florian Camps belongs to Aero, who is from Aero. You will receive them in our lab November. It's an amazing group. They've developed the puff-in. This is a Penelope application. If you are from simulation, you don't like it because you know it's hard. You cannot work on Penelope there. This is a software. It's hard to develop, but it's amazing because it calculates. It shows the whole dose distribution, and we can optimize the design on how it will be radiated. So it brings 3D geometry, so we will radiate to sterilize the syringe. So if there's a needle, is different because the needle is different from the syringe itself. So it brings the 3D geometry with AutoCAD. So it's easy to use, but this is a preliminary analysis tool because it's it's not so flexible. Because it will say, now you do this, now you do that, now you put that data. So we know that those who work with that are passionate about challenges. I went to a congress. It was a lecture from Professor Florent, September 2024. Actually, September 24, 2025. So it's quite recent. So we brought the computational dosimetry, but made by a group of physicists who work. So we have dosimetry 2, from physical dosimetry to e-dosimetry. And why electrons? Because those who work with experimental field, we find many problems with electrons. So I talked to him. This is part of his presentation. I got interest and I know nothing about simulations. So I know the software is Jump 4. You can see Penelope here, MCNP. I will not dive into that because this is not the goal here, but just for you to have an idea. So here we have the amount of softwares used to understand what happens when radiation interacts with the material. But they may design the product and packaging, the operational qualification of the facility, the process qualification. So we can check that box. What is the minimum, the maximum, where I will put my routine dosimeter? It will be in the middle. Okay, but in the box, okay, we've changed the type of the box. We have the wrong box type. Am I going to analyze everything again? I don't have time for that. If the simulation is validated with my experimental results, I can at least try to guess the result. Is it possible to calculate absolute dose? This is a dream, but we are not sure yet. And why? Well, they're not sure because the simulation data validation is based on the experimental results. So we need to join effort. They need the entry data. And who provides that? The experimental physicist. So trusting the simulation results may be biased by data. So once we interact and checking, well, we will shock session, particles, journey. So that's why part of my graduation and my background is on experimental nuclear physics. So it's amazing. I love. When I saw that, I thought, oh, we are playing with physics. So that I have this transition that is a great challenge. But this demands training, professionals that goes back and forth from the industry and the academy. So we need to train our human resources. Eros is here. He was in my last lecture. And I've closed that lecture with a challenge to the audience. If there is anyone from the physics who loves simulation, it doesn't need to be high dose simulation, but preferably PhD, cannot be a student. We cannot wait 2 years for that. I have a postdoctorate scholarship to be provided, and I've been waiting for 4 months to find a candidate to be there in my group. We have Dr. Josimeire, my huge partner on this field. And here, these are the standards and the guidelines, not only for health, medical field, but I had a special view for food, dosimetry for food, and polymethylmethacrylate. You have it all here. And here, of course, I need to thank Floret Kantz, who is being a great partner and is being great on this work. Of course, I also talked to Professor Gerardo, who gave a speech here, and I told him, should I talk more about that? And he told me, okay, take care. Do not disclose too much. No one knows about this dosimetry. I hope you have enjoyed this lecture. We have a challenge here. Some people think, I have nothing in my life. No, you always find a problem when you look for them. So it was a pleasure to be here.
Muito obrigada.
Thank you, Dr. Carmen, for your amazing lecture. I'm pretty sure We all have learned a lot about this technical field. Dosimetry is so important. Due to a lack of time, we won't have time for questions. But to ensure that all questions are cleared, the questions will be sent and forwarded to Professor Carmen, and she will answer later on. Thank you very much. Thank you, everyone. Thank you, Camila.
Obrigada, Camila. Obrigada, doutora.
Thank you, Camila. Thank you, Doctor. In order to respect our audience, we will try to connect once again with Professor Marie. We ask you to wait patiently as you're doing so far. Thank you.
Agora, passador, ela entregou o passador? Ah, tá com ela.
Hello?
Dr. Marie?
Yeah, I'm here.
Isso.
Yeah? The sound is good?
Yeah, it's good.
It's great.
Vemos que ela está mais animada.
Great. We got there.
Oh, sorry for all my technical problems.
No, we are more than happy to have you here, to have you with us. Okay?
Yeah.
Coloca
Do you
na
see my
tela.
screen?
Yes, we are going to put your image on the screen right now.
Is it okay for you? You see it?
Muito
Yes,
bem,
we can see
muito
it.
bem.
We can hear you. And we'll ask you to start immediately the presentation so that we can gain some time, okay?
Okay.
Recover some time.
So,
Please.
thank you very much, and sorry again. For my part, yes, I will focus on the need to properly control the organoleptic and microbiological quality of irradiated food for certain application. I've just one slide to present very quickly Aerial, because Aerial is a private R&D organization designed as a technological research center. And we are involved in industrial radiation application and process control for more than 3 decades. So I can speak about our dosimetry activities because we are accredited as a secondary standard dosimetry laboratory. We have also lab for detection of irradiation food, which is also accredited. And we have our own microbiological labs, class 2 and 3, physiochemical lab, and sensorial analysis lab. And I am involved with these parties because it's the reason why I'm here. You know why food irradiation consists. So I passed quickly on that. And you see before that whatever is the used technology, E-beam, X-rays, or gamma ray, the key parameter is the dose. The dose deposit in the product. And what I want to speak with you is about what is the key for a successful treatment. Because you must define what effect is desired. So that's the purpose of the treatment. For example, between microbiological, physiological effect in the food, This should make it possible to define the minimum dose for the targeted desired effect to be effective. That's the minimum dose, the dose to be effective. And how and why does it work? I want to come back and just a little explanations about how is it work. You know that ionizing radiation acts on molecules in two ways. So you have the direct action of ionizing radiation on molecules, and this the probability to modify the molecule is depends on the dose and also on the size of the molecule. So as DNA is so big, if you compare to a molecule of glucose or water, for example, that's the first reason why you have more action on DNA than on the other constituents present in the food. And the second action is an indirect one by the free radicals product in the food, and which are responsible to about 30 to 90% of the damage on, to the DNA molecule. So here you have a representation of the direct action on the DNA molecule, and generally the microorganisms that are sensitive to radiation cannot repair those double strain breaks. That's the direct effect. And the indirect effect is represented here because the more important one was radiation interacts with water, leading to the formation of those free radicals, especially hydroxyl radical. Those free radicals can diffuse far enough to reach and damage DNA. Those radiolysis products is the percentage is very low, and they are very short-lived, but they are highly reactive if they are here. So you see here, the more complex are the DNA molecules, and you can see that with molecular weight in particular, the more sensitive is it to radiation by direct action. So here you have a scale from viruses to, for example, sprout cells with bacteria, yeast, molds, and insect parasites. And you can have a sort of scale of resistance to radiation from sprout cells, so in the inverse of the I showed you before. So schematically, the resistance to radiation is higher when the size of DNA is smaller. And in the middle, you have the field of bacteria, yeast, and molds, what is interesting for decontamination. So here, in relation with this scale of application of resistance, you see here the application with the very low doses, like sprouting inhibition or phytosanitary application. And in the middle of the scale of doses, you have here sanitary application. So you see what are those desirable effects with the increasing dose ranging from a few 10 of grays to a few tens of kilograms. You have the effect ranging from sprouting inhibition, for example, to sterilization. So you see the domain of application of decontamination is the domain of doses between from 1 to 10 kilograms. So why microbial decontamination is very interesting? As the first application in this field is to kill the pathogenic bacteria. Here you have the representation of the top 6 of food germ causing human illnesses or outbreaks in USA and Europe from recently. And the top one is Salmonella with Campylobacter, present in mainly in animal foods. But you have also E. coli, the special one, very toxinogen E. coli, then Clostridium perfringens, Yersinia enterocolitica, and then Listeria, more present in cheeses or fish products. And what is interesting here is that most of those pathogenic bacteria are known as sensitive to radiation. You have some figures here in this table with D10 or DRD. That's the dose required to inactivate 90% of the microorganisms initially present. You see here, for example, for Campylobacter jejuni, it's about 0.5 kilograms, like for E. coli, very sensitive to, or Chronobacter, which is very close to Escherichia coli. And the same for Salmonella or Yersinia, very, very sensitive. And you see that the most resistant are the spores of some bacteria, like Clostridium botulinum, perfringens, or Bacillus cereus. The G10 is higher than for the other type of bacteria. What I want to share with you is the necessity, if you want to extend the shelf life of a product or to eliminate specific pathogen, as we see before. In those two cases, that should not be used to hide poor quality products or inadequate hygiene practices. That's very important in Europe because Europe is so strict with hygiene management practices, and the regulation also is very strict. Here you have an example in France. We have an authorization for ionizing deboned chicken meat. The purpose is to be safer against Salmonella, but the regulation said before treatment you must have no Salmonella in 50 grams of product, like the other product. And after treatment, you must have no Salmonella in 50 grams of product. So you see, the irradiation is used to be safer than in the normal regulation. It's not to kill all the Salmonella could be present. So usual doses between 1 and 10 kilograms, depending on the food initial microbial contamination. That's the reason why with the rigorous hygiene management practice, you can control your microbial initial contamination, and so you will be more efficient with irradiation. It depends also on the food compounds, particular with the presence of water, and it depends on the treatment environment. So for this part, two parameters are especially important. The presence of the availability, water availability in or around the food. And I showed you before that it's because of the free radicals coming from the water that you can have less resistance of microorganisms if you have free water around the DNA. So if you freeze or you dehydrate the matrix, then you increase the radio resistance of the microorganisms. You have an example here with Salmonella. And you have the same thing with oxygen. So if your atmosphere in your packaging is oxygen, air, normal air with the presence of oxygen, you decrease the resistance of microorganisms. And if you are under vacuum or under modified atmosphere, the microorganisms are more radio resistant. Okay, that's for the lower, the minimum dose, and for the maximum dose, because you have a maximum dose for each product. This maximum dose is could be the first limit could be organoleptic changes. That's more current, but you can also have nutritional changes. So this dose is the limit of the treatment. Some example of possible effect on the food, possible negative effects on the foods. You can have degradation of some nutrients, and for example, vitamins and lipids are more sensitive to irradiation than proteins or carbohydrates, sugars. So you understand that if you have, for example, deterioration of vitamins, only some of them, and not all the vitamins. The more sensitive are vitamin A, B1, C, and E. If you have some deterioration of lipids, the first consequence is could be a problem of odor with in the more fatty foods. You can have also change in flavor. It's the same for odor with aroma produced by oxidation of the matrix. But you can also have change of color or of texture if you change, especially if you have degradation of proteins. So all those organoleptic or nutritional changes are a consequence of direct and indirect effect of radiation, like for the inert microorganisms. So to determine the maximum dose, just focus of the mean, you can use descriptive analysis, sensorial descriptive analysis, and we do that with a trained panel of 10 to 20 to around 10 subjects, trained subjects who are called experts on the studied products, and they are here to study the differences with the non-irradiated product. So the experts say, yes, we have a difference, or we have not. And the consumer, So for to have the perception of the consumer, you need to make the study with 100 consumers of the studied products, and they can say if their preference, if they compare to the non-irradiated one product. But if there is slight differences, they can, you can measure the acceptability. Perhaps you have a slight change, but it remains acceptable for the consumer of the product. We can also use the consumer panels to test the acceptance of irradiated foods. It's different because here we test anonymous products. We don't say that they are irradiated. And if you label, you show the label of the product, you can compare and see the effect and a real acceptance of the product. So here, I hope I will be clear enough. I have to say that the process is safe. So you have any toxic residue, it's effective, it's well studied. You have a lot of experimental studies, existing studies. But a lot of time you need a validation for your own product if it's not exactly the same that in other studies. The first consideration is to have a clear idea of the purpose and to know that it does not replace hygiene or good manufacturing practices or good agricultural practices. And it's always a compromise between the maximum dose of irradiation to preserve the food quality and the minimum dose of irradiation to be efficient, to be efficient in regard to the purpose of treatment. And you must be careful with the environment of treatment, with the packaging, the storage and transportation. And so sometimes irradiation may not be possible. It's not it's not always possible. That's my message. Thank you for your attention. If you have questions, I'm sorry again for those problems. I think it's time for lunch for you, so I hope it will be fine.
Thank you so much, Dr. Helena. Tem alguma pergunta? Pode mandar, inclusive para...
Sorry, I don't hear you, but...
we don't have time, but
I hear you.
Yeah, but the questions, if they can send to you, and then you can answer. Yeah, could be this way.
Yeah, sure.
Yeah, okay. So we want to thank you again, please. Thanks. Obrigada.
Okay. Obrigada.
Thank you, moderation of Professor Psy. So let's move with our agenda. We are happy to be able to show all the content that we promised. So now we will invite Almirante Brazil to introduce the subject, opportunities and challenges for the installation of X-ray irradiation centers.
Bom, inicialmente eu vou ser muito rápido.
I will be very fast, actually, mainly due to time. So I'd like to thank everyone. So Commander Veloso, the team, Dr. Patricia, thank you for helping us and assembling this event that was so useful. I'd like to thank all the speakers, Dr. Constance, Dr. Hortensia, Dr. Carmen, Dr. Tsai, someone who I may be missing, Dr. Ana Lucia, she's there. Some very important people we have with Dr. Andrea, Thiago Rossin from GSI. Yesterday we had a representative from the GSI. I cannot miss this opportunity to talk about Amazon as we are hosting this event. I can see some people that we have invited to be here, and maybe they do not know our company, so it'll be quite fast. Amazon is a nuclear technology company, a state-owned company that works towards Brazilian society. So we have a huge nuclear footprint. We work on decarbonated energy, clean energy, Angra 1, Angra 2, and if God allows us, Angra 3. No, I don't need to talk about food irradiation. We've been here for 2 days talking about this. On the full life cycle, we work on almost all the cycle except for prospection, because this is not our expertise, but mining, conversion, uranium to LOK conversion, gas conversion, enriching uranium, we have a great footprint. Fuel producing and fuel consumption for energy and nuclear, and when discharging this fuel on nuclear, we have the prototype of the embarked plant, radio pharma. We have a great partnership with the PEN and RMB, where we have been doing everything we can so that RMB can be a reality. It will bring great benefit for our society. SMRs on energy generation. We are attending all forums so that we can understand all the initiatives around the world. There are more than 100 initiatives around the world. We are trying to understand, and we want to participate on all types of implementation that we have in our country. And nuclear medicine, we have this initiative to have the first proton therapy center here in Brazil. And then energy transition. We work with Brazilian private companies in order to replace polluting energy source and replacing them for clean energy, so mainly SMR. So this is Amazon. Let's talk about our subject, the opportunities and challenges that we see for implementing this type of technology in Brazil. Well, it seems that I went to future. I've watched all the lectures and I came back to present mine. This is not true, of course, but every speech, every lecture, I could see part of this summary that I'm presenting to you. So I brought 4 main points. First, technology applicability. The second is the legal framework, both international and national frameworks. Third, the public acceptance. And lastly, cost, financing, funding. Let's start with the application. We've just heard Professor Marie that in spite of the studies, sometimes it's not possible, because in each case is a case, and we heard from that. We have proteins, fat proteins, the climateric and non-climateric fruits that need to be handled differently. We have fruit size, water, amount of water, We have spices that are still little explored. We have grains. We are large producers of grains and need to explore the possibility of using this technology on grains. And then for phytosanitary treatment and extending the shelf life. We can discuss it all, and we need to approach the potential users so that they understand the benefits of the technology, so that they can put that on their business models and evaluate the possibility of investing on that. So our legal framework. Well, we have polluted this slide on purpose because actually we have an infinity of international, national legislations that demands from us a harmonization that actually does not exist. So investors that will invest in Brazil needs not only to adhere to Brazilian regulations, but international transport regulations and the target country regulations. And many times this is the challenge. For example, the European Union has several restrictions for doses and some elements. And we could see that there is exponential growth on application both Latin America, Mexico, and Asia. So it is unbalanced, and this imbalance becomes an opportunity, a market that accepts this type of technology. Some markets accept it more than others. So we have the fourth item, the public acceptance. So we have three provocations here. Yesterday, Dr. Ariadne quote one of the outcomes of iFish, that most of the participants raised public acceptance as a barrier for applying the technology. People would be biased, or they have a lack of knowledge, and therefore avoiding irradiating products. It may be a lack of knowledge or bias. We've been working hard on that sense. We are part of a social communication network for nuclear industry. Our communication assessor, Alessandra, leading this team. And they've been working hard on that sense, and we've been trying throughout all the events that we attend to clarify the public opinion and mainly the potential users on what we've been talking about. So here I bring two examples on what we've been doing.
Moldar futuro brilhante. Na agricultura, a tecnologia nuclear tem revolucionado a produção de alimentos. Cerca de 1/3 da produção mundial de alimentos é perdida ou desperdiçada por falhas na produção, conservação, armazenamento e transporte. Na produção dos alimentos, a tecnologia nuclear permite o uso de técnicas de manejo de água em ambientes áridos. Sensores de nêutrons medem a umidade do solo e das plantas e, através da técnica de irrigação por gotejamento, fornecem a quantidade exata de água para as lavouras. Por meio da identificação da assinatura isotópica de gotas de chuva, que são como impressões digitais das moléculas de água, cientistas podem rastrear a origem, o movimento e a distribuição da água na atmosfera, no solo e nas plantas. Entender esses processos ajuda a otimizar o uso da água na irrigação, identificar fontes de contaminação e desenvolver estratégias para a conservação da água, garantindo a disponibilidade desse recurso vital para a produção de alimentos. O tratamento de alimentos com radiação aumenta sua vida útil, reduz a carga microbiana e inibe o brotamento em produtos como alho, cebola, inhame e batata. Os alimentos mais sensíveis a manuseio podem até ser tratados em suas próprias embalagens. Isso reduz as perdas na produção, armazenamento e transporte, permitindo alcançar mercados distantes e atendendo aos requisitos fitossanitários para exportação. Essa tecnologia não compromete a qualidade nutricional, textura ou aparência dos alimentos. Diminui os níveis de contaminação por micro-organismos, minimizando o risco de doenças entre os consumidores e reduzindo o uso de agrotóxicos nocivos ao meio ambiente. A radiação segura pode ainda ser usada para criar plantas mais resistentes a doenças e pragas e mais tolerantes a secas e inundações. A irradiação de alimentos está alinhada com o Objetivo de Desenvolvimento Sustentável da ONU número 2, que visa erradicar a fome, alcançar a segurança alimentar, melhorar a nutrição e promover a agricultura sustentável. A Amazul é uma empresa de alta tecnologia nuclear que reúne conhecimento para atuar em várias áreas que promovem a saúde e a qualidade de vida dos brasileiros. Maior empregadora de engenheiros nucleares do país, está envolvida em uma ampla gama de projetos de tecnologia nuclear, que incluem consultoria, planejamento, assessoria de licenciamento, engenharia, gestão de qualidade, aquisições, construção, montagem, fiscalização e operação. Recentemente, a Amazul recebeu o reconhecimento como instituição de ciência, tecnologia e inovação, abrindo novas oportunidades para expandir nossa atuação e participar de projetos estratégicos adicionais. Para reforçar ainda mais nossas soluções no setor nuclear, desenvolvemos uma metodologia premiada de gestão do conhecimento, aplicável em diversas organizações. Nossa equipe talentosa e dedicada está comprometida em impulsionar a tecnologia nuclear, liderando o caminho, explorando novos horizontes e construindo um futuro mais seguro e sustentável para todos. Junte-se a nós na jornada da inovação e excelência, moldando o futuro com a tecnologia nuclear. Amazul, tecnologia nacional em benefício da sociedade.
Então temos usado esse.
So we've been using this type of videos on shorter versions as well to approach people and to clarify questions for the general public. But when we talk to the stakeholders, what we call the potential market, potential customers for this type of technology, sometimes it is hard to bring them to a radiation center. Those who don't know, they struggle to understand the size of those projects and what we do. So together with the technical board, we have a different video with a different objective. So this is a virtual sketch where you can walk through a irradiation center. It doesn't need to be this size, but it shows everything that must have in a radiation center. So here is the cold chain. We will see the radiator palletization, pallets being irradiated in a more dynamic way. In the future, we will have a character called Urania guiding this visit, because in the future, who will narrate and tell the story about this video will be this character, this called Urania. So if you will, you can access our YouTube webpage where we have some chapters of Urania already talking about food irradiation, but also talking about nuclear technology, demystifying and bringing to the young generations the use of nuclear technology. So this is the entries. Then back then we have the cold chamber, pallet storage, the trail. You can see the cold air there, that numb. It will be improved together with Audira Thank you, Audrey, for your effort. I know he likes to do so, so it is a quick video, only 2 minutes video that allows a person who has no knowledge on that to have a better idea on what we've been talking about. This is the banker, the palette pathway, the irradiator. It allows us to show not only by pictures, but some manufacturers provide some designs. This is a more dynamic way, and then the treated pellet goes to the cold chamber to be stored.
Now, the last subject, which is costs. In our point of view, this is of the greatest importance, the financing. No, we were talking about the financing or investment scale, operational expenditure, and also touch on return of investment. We talked about Dr. Geraldi mentioning this.
Yeah.
Every product will have a different type of a treatment. Yesterday, we talked about multi-purpose centers where you can, during the harvest, work on some types of products, and out of harvest, you can go to other products. So our continental scales many times will demand a greater number of centers and install them in ports and airports could be the best approach.
Seu próprio negócio. Isso.
But if your scale is so big, you can have one or more centers for that. So, ladies and gentlemen, thank you very much for this opportunity to present you those provocations. And it's a great pleasure to see this room full at this time. And now we give the floor to our president to close our workshop.
Chegamos aí ao encerramento do
So this is the closing of the workshop. 2 days of intense exchange of knowledge, debates, reinforcing the collaboration among experts. We now can transform this knowledge and concrete actions that will consolidate the safe and innovative use of nuclear technology for the benefit of our society. This meeting was an important step to integrate Brazil with the other countries in Latin America. We thank all the speakers, moderators, institutions, and participants who contribute for this meeting. I'd like to invite Admiral Milton Costa to close this event. So please remain in the room later on for a picture. Well, good afternoon. I'd like to thank all of you, all of those who participate in this event, whether in the organization, which was not simple. This is a complex event. We have people coming from our own country and from other countries, and it's important to have those people here. We have a great advantage. We are with the entire area that develops the technology, the area that needs this. the commerce, the industry, and we have this connectivity between the company and several sectors. So such an event has a special purpose to close the links of this chain, because we do have the technology, we have the knowledge, and we are advancing even more, not only here in the country, but all over the world, up to date with the technology in the radiation area. We know it already. We have the need. We have agrobusiness, which is huge, one third of our GNP, that produces not only for the domestic market, but to export and to have the efficiency and to reach several goals. And following the United Nations goals, we are participating in this. So we have many people who are dreaming and struggling to develop their sector, whether commercial, industrial, technology, but we need one link is missing, the financial link. The greatest difficulty we have to foster this sector in Brazil is the financing ways for this sector. And we at Amazon, together with several partners, we are trying to open doors so we can proceed. We need to shake the private initiative and also the government, because we have two packages. One is very important, the pilot irradiation center. It is necessary for the other centers. Who is going to test, to run the tests? Who is going to study each of these items? Is it possible to radiate? How much? What is the minimum, maximum limit? What is the quantity? What is the logistic necessary for that? Well, what I can tell you is that we are fully qualified to do the technical feasibility studies for each of the things presented, but the cost varies, time varies, the return. So the pilot center will be extremely necessary, and the people of IPE in other sectors, we are doing well. We need the resource, but we will get there. But we need to open the doors. Where should they install the center? Oh, at the port, airport, the source with the producer. We need to have a deeper study for technical feasibility. The port is where the product goes out, but how to get there? If you take to the container in a truck to arrive at the port, and when it gets to the port, you have to take out the product to irradiate. So for each product, we need to think. We do have a very good business model that can be adapted to any type of product. It is feasible, both in technological terms, the analysis we need to run, and we saw Mexico's example. This is extremely profitable business, provided we overcome cultural barriers, the prejudice, and the private investment. It's not easy for a company or a group of companies to make such an investment without knowing the return on investment. I heard from some sectors, Admiral, okay, we are going to invest, but my harvest is already sold for the next 2 years. What will I gain if I irradiate now? So we need to think. Every case is one case. So this discussion was very good, mixing all the players here, each of them with their vision. The businessman needs to know about the technological challenges involved, and we need to be together. So this was very good. I'd like to once again thank all the participants in person or virtually. I've heard several comments, and this is worth. When we believe in a project, we need to do the best, and we did that. People did their best with several players, but what is interesting is to know what is the word, the phrase that we can get out of here. It was worthy. The next we'll do. And the next we will bring novelties. And we need to leave our comfort zone. The technological sector has its comfort zone. The industrial, commercial sector also have their comfort zone. But they know they have a good business, it's profitable, so that's a good zone. Could it be better? Well, so once again, thank you very much. See you next time, and I hope to see the friends coming from abroad. We have the same difficulties as other countries. We all face the same problems, and I'd like you to think about it, okay? Because this was worthy. Thank you.
Pessoal, eu acho que a diretoria executiva.
Well, the executive board would like to take a picture with this audience. So please come to the stage. Part of the people can be here on the stage. Those who spoke, and here we can go down the stairs and to have the picture. Thank you.
Pessoal, vem vindo aqui para frente, por favor. A gente vai se acomodando, vai se organizando. Podem vir. Podem vir subindo aqui também, pela escada aqui nos fundos do palco, quem for mais alto. Os mais altos podem ocupar aqui a parte de trás do palco, ainda tem espaço. Tem bastante espaço atrás do palco. Podem subir. Vamos nos acomodando. Um pouco na frente também aqui do palco. Podem vir para a frente do palco, em frente às cadeiras. Tem espaço em frente às cadeiras. Vamos fazer 2 filas aí embaixo, quem está em frente às cadeiras. Podem fazer 2 filas. Por favor, o fotógrafo pode sinalizar. Uma salva de palmas.
Obrigado lá.
Muito obrigado.